In section 14.5, we want to think about the synthesis of ethers. How do we make ethers? Now, there's two modes of synthesis, or routes basically, we want to discuss here. You've got the Williamson ether synthesis, and then you've got the alkoxymercuration demercuration procedure, which is more academic because of the environmental regulations of mercury, the toxicity, and you don't want to be using mercury in a pharmaceutical synthesis because that drug is going to be used in a human, and there's additional requirements for making sure there's no mercury in the product. So, but it's in the textbook and we'll talk about it. So what is the Williamson ether synthesis? The Williamson ether synthesis is a two-step procedure. Starting from an alcohol, we convert that to an alkoxide. Now remember that alkoxides are very strong nucleophiles and suitable for nucleophilic substitution reactions. In the second step, we would want to add an alkyl halide to this. Let's use bromobutane, and this will form an ether. Okay. Now, how does this work? In the first step, remember, we have an alcohol that reacts with hydride, which is a strong base, and that's going to deprotonate the alcohol to form the alkoxide. Okay. In the second step of the mechanism, when we add, the alkyl halide, that's going to perform a substitution reaction by an SN2 reaction. So the negatively charged oxygen is going to attack the alpha carbon and kick off the halide to form the product. Okay, and that happens in step 2. Now, the thing to remember is that for SN2 reactions, primary alkyl halides, methyl and primary alkyl halides, react most efficiently, better than secondary, okay? And definitely, we don't want to try any substitution reactions on tertiary, okay? So, when you're planning your synthesis, for example, and you're deciding how to make this ether, we have two possibilities, okay? Our alkyl halide can come from this portion on the left side of the molecule, okay? And that's not going to be a good choice because this negative charge, although we can draw it, is not going to be able to displace a tertiary halide in a SN2 reaction. Okay? That's not going to happen. So what we want to instead do is think about making our alkyl halide from the other substituent. And that is a good possibility because we know that substitution reactions can happen on methyl halides very well to give you the target molecule. Okay? So when you break it down, you want to choose the more substituted alcohol. You want to choose the less substituted alkyl halide. And then you want to use these two steps up here. You want to take your alcohol and treat it with sodium hydride. And then step 2, you want to indicate adding the alkyl halide to the intermediate, reaction intermediate, to give you the product. Okay? So let's see how this works with problem 14.5 in the Klein book. Here we have in part A a cyclohexyl group, and that's a secondary carbon. And we have this isobutyl group here, which is a primary carbon. So remember what you want to do. You want to select your more substituted alcohol. So we're going to start this synthesis with cyclohexanol. Okay, and you want to treat this with sodium hydride. That gives you the alkoxide, which is a very good nucleophile. And then in the second step of this synthesis, you want to add your alkyl halide. You could use chlorine, bromine, or iodine for your leaving groups. I just tend to go middle road and pick the bromide, okay? And this will give you the final molecule. Okay. If we did it the other way, it would be less efficient, okay? So this reaction is SN2, so we choose the primary alkyl halide, okay? That's my explanation for my choice. In molecule B, we have a primary carbon right here, and we have a secondary carbon right here. So again, we want to choose the more substituted alcohol. So I'm going to choose isopropanol for my alcohol. I'm going to treat this with sodium hydride, and that will make the alkoxide. Okay, the alkoxide. And then what I want to do is add the alkyl halide. I want to include all of these carbons, including that dotted blue one, and I'm just going to have a leaving group, a halogen, attached to that carbon. So I will draw in my 6-membered ring, draw carbon, and then I'll draw iodine as my leaving group. And that will give me the target molecule there. I'll just recopy it all up here. Okay. So more substituted alcohol, less substituted alkyl halide. So again, it's SN2. So we choose the primary alkyl iodide. Okay. In part C, examine carefully what you have. This is a tertiary, and this carbon is a methyl. It's not attached to any other carbon, so it's just a methyl. So we want to start with our more substituted alcohol, which is going to contain a 6-membered ring, a methyl group. Okay. And we treat that with sodium hydride. Sodium hydride will react with all alcohols with simple efficiency. O- here. Okay, so it's a rather bulky base, but that's going to now attack in second step methyl bromide. Let's use methyl bromide or bromomethane, and that'll give me the target molecule, and I'll just copy the product here. Okay. So remember, a methyl is just a CH3 group. So that gives you an idea of some basic types of problems you'll encounter with the Williamson ether synthesis. Okay. The second way to synthesize ethers, as presented in the textbook, is through something called the alkoxymercuration-demercuration procedure. Previously, in chapter 9.5, it says here, we learned the hydroxymercuration-demercuration procedure. Okay. A review of section 9.5 might be useful for you, but basically we're adding water across the carbon-carbon pi bond in a Markovnikov fashion that avoids rearrangement. So the OH goes on the more substituted carbon, and the hydrogen goes on the less substituted hydrogen. The rich get richer. Okay, so if you have a hydrogen, more hydrogens on one of the carbons, that carbon is going to get the hydrogen. Okay, so if it has more hydrogens, it's going to get the hydrogen. That's Markovnikov's rule in a nutshell. Okay, and the OH goes on the other carbon. Now, the alkoxymercuration-demercuration procedure . is shown here in section 14.5. Instead of using water, you're going to use an alcohol, and you can use any alcohol you want. Butanol, 2-methyl, 3-ethyl, 1-hexanol or some crazy thing like that. Any alcohol would be fine, even cyclohexanol. So the OR group of your alcohol is going to attach again to the more substituted carbon, and the side with more hydrogens gets the hydrogen. So let's see how this works here with this reaction here. Okay. So again, what you need to do is identify the 2 carbons of your pi bond, and you come over here and you identify those 2 carbons, and you see what's been added. This is an OET. So that's going to come from ethanol. Okay. Now the reagents you want to use for this are going to be mercury acetate, ethanol. Okay, so that's where you put your ethanol. I'll make it in yellow so it stands out here. So this is the key difference here. That's where your ethanol is going to be. And then step 2, that's where you do the sodium borohydride. Okay. The use of mercury in the sodium borohydride, what it does and everything, is explained in section 9.5. But here I'm just focusing on, filling in the correct reagents. Now in B, let's do the similar analysis. We have our carbon-carbon pi bond. You identify where those 2 carbons are, and you see what's been added. We're adding an isopropoxy group. So that comes from isopropanol. And so our chemical reaction would look like this. Mercury acetate. And I'm just going to draw the structure, isopropanol. And step 2, we're going to add sodium borohydride. Okay. And that's going to give me the target molecule. This is the target molecule. Okay, let's keep going. So in part C, here are my 2 carbons. I'm just adding a methoxy group, so that comes from methanol. So the reagents here would be cyclopentene, mercury 2 acetate, and we want to add methanol. Okay, and step 2, don't forget that, would be sodium borohydride. Okay, and that would give me the ether there. Cyclopentyl methyl ether. All right, some of these ethers can be quite complicated. Here's a more complicated one, I would say. So what are we adding? We're adding this alkoxy group, and that's going to come from cyclobutanol. Okay, just add an H to your group there that you've circled, and that comes from cyclobutanol. So that's the alcohol we would be adding. So the synthesis would be to take our starting 1-methyl cyclohexene, add your mercury 2 acetate, add the cyclobutanol. Step 2, work that up with sodium borohydride. Okay, and that would get you the target molecule. Now in the textbook, I don't think they have these problems. They might have them in the back of the chapter. But how would you make this sort of molecule? I'm having trouble drawing a pentagon here. Now you might be thinking, oh, well, I'm going to do the Williamson ether synthesis. But if you analyze this carbon on the left has a tertiary carbon This carbon on the right has a tertiary carbon, and we know that we can't do substitution reactions by SN2 chemistry on a tertiary carbon because it's too sterically hindered. Instead, elimination reactions occur. So we need to do a alkoxymercuration procedure. So we identify the two carbons that we want. We identify the alkoxy group. And when we break this down backwards, we propose that we start with this alkene with that methyl group still up there. And we propose that we use tert-butyl alcohol. Okay, so these would be the starting materials. In the forward synthesis, it would look like this. We would take 1-methylcyclopentene. We would treat this with mercury 2 acetate and tert-butyl alcohol. Step 2 would be sodium borohydride, and that would get me the desired target molecule. Okay? So think about synthesis now. We can make things in a lot of different ways, and I hope this gets you started. All right? Thanks for watching.